Alright, so we will be talking about cardinality today, and so it's cardinality. And as we know, the cardinality of a set is essentially the number of elements in a set. So for example, if I have a set A which has the elements 1, 5 and say 7, then the cardinality of A, it's written A with two bars on two sides, is 3 because there are three elements 1, 5 and 7 in the set. Again, if I have another set, say B, and that has elements say 2, let's pick say 9 and say 3. So once again there are three elements in the set B, so the cardinality of B is once again 3. So we can just compare the cardinalities of the sets A and B after we have written it down here. In this case both are 3, and say that the sets A and B have the same cardinality, right? So the cardinality of set A equal to cardinality of set B equal to 3. So that's the usual way of comparing cardinalities. But there is a slightly more contorted way of comparing cardinalities of sets, and this is how it goes. So we can look at the two sets, so in this case sets A and B, and try to establish a one-to-one correspondence between the elements of the sets A and B. Right? What do I mean by that? For example, here in between set A and B, I can try to create that one-to-one correspondence. I can match up 1 in set A with the 2 in set B, say the 5 in set A with the 3 in set B, and 7 in set A with the 9 in set B. So I end up creating a one-to-one correspondence between the elements. Right? So and that tells me that the cardinalities of the sets A and B are the same. So if this cardinalities were different, if there say B had 4 elements, let's pick an example. So let's say pick let's pick C. Let me change the color of the stylus. Okay, so in say we have C equals 1, 3, 5 and say let's have 8 in here. And if I try to establish a one-to-one correspondence between the elements of set B and C, then what will end up happening is that say I pair up 2 with one of the elements, say 2 with 3, 1 with 9, and then say 3 with 8. But since C has 4 elements, we cannot pair all the elements of C with the elements of B, so something will be left out in the set C, right? So this tells us that the cardinality of B is not same as the cardinality of C. Of course, in this case we don't have to really do all that, and we could simply write down the cardinality of the set C equals, which is equal to 4, and then clearly C, the 4 is not equal to 3, so the cardinality of C is not same as cardinality of B. But being the same fact can be told in the slightly contorted way, where we say that A and B have different cardinalities because one fails to establish a one-to-one correspondence between the elements of the set B and the elements of set C, right? So let me, if I can write this down here. So the cardinality of A equals cardinality of B, and which is not equal to the cardinality of set C. right? And the way we did using one-to-one correspondence is that we could establish a one-to-one correspondence between the elements of set A and B, but we failed to do that between elements of set B and C, right? All right. So now the question is, if we can write down the cardinalities as numbers, say 3 or 4 in this case, why should we be doing this one-to-one correspondence thing? Why is this useful? Well, this is useful when the sets A and B are not finite sets, if they're infinite sets, right? So then we cannot write down the cardinalities as numbers like 3 or 4. Of course, we can write the symbol infinity, but very often that is uninformative. So let's look at a few examples. All right. So let's consider the set of natural numbers. So as we know, the set of natural numbers is the set containing 1, 2, 3, 4, and all the positive integers, right? So that's a set of natural numbers. Let's consider another set, S, which is almost the set of natural numbers, but I will remove the element 1 from it, right? So it's all the natural numbers greater than 1. So it contains 2, 3, 4, 5, 6, and so on. So if I now try to write the cardinality of the set of natural numbers, let's write that. That is infinity, right? Now if I write the cardinality of S, that's also infinity, right? Likewise, if I write the cardinality of the set of integers, that's also infinity. If I write the cardinality of reals, that will also be infinity. So infinite sets like this, natural numbers, the integers, the reals, the set S, if we try to write the cardinality, we are stuck with one symbol, which is infinity, right? And this is very uninformative. So the question is, can we distinguish between different types of infinities? So can we say somehow that one of these infinities is greater or smaller than one of the cardinalities of one of these sets is greater or smaller than the other? So that's where in infinite sets as this, the method of comparing cardinality that we just discussed by establishing one-to-one correspondence between the elements of the sets, this is where that definition comes to use. So let's try to look at these two sets that we have written down. So the sets S and N, and one can actually establish a one-to-one correspondence between the elements of sets N and the natural numbers and S. So here I can pair up 1 in the set of natural numbers with 2 in the set of set S. So that's my first element pairing. Then 2 in the natural numbers with 3 in the set S, 3 in the natural numbers with 4 in the set S, 4 with 5, and so on. So if I write the set of the natural number, if I have a natural number which is n, lowercase n, I can pair it up with n plus 1 in the set S, right? So 1 is being paired up with 2, 2 is being paired up with 3, so it's n plus 1, right? So that's the correspondence. Likewise, if I have an element m in my set S, it can be paired up with m minus 1 in the set of natural numbers, right? So the important thing to note here, however, is that this pairing is 1-to-1. That means nothing is left out and nothing is counted more than paired up more than once, right? So for every natural number n, right, there is a unique n plus 1 in the set S, and this doesn't leave out any element in the set S, right? So natural number 1 pairs up with 2, natural number 2 pairs up with 3 in S, 3 pairs up with 4, and so on. Everything gets paired up in S, right? And likewise, no element in S is paired up twice with two different elements in the natural numbers. It's a one-to-one pairing, right? Likewise, we can see that for elements m, m minus 1, m in S, m minus 1 exists in the natural numbers because S starts at 2, and and for every element m, m minus 1 is unique, a single unique element in the set of natural numbers, and everything in the natural numbers are paired up. So this establishes a one-to-one correspondence between the elements in the set of natural numbers and the elements in the set S. So this tells us that the cardinality of the natural numbers is equal to the cardinality of the set S, right? So this is kind of interesting because natural numbers is, of course, the set of natural numbers. There are infinitely many elements in the set of natural numbers. In the set S, we also have infinitely many elements, but S contained one less element, right? So it didn't have the element 1 in which was there in the set of natural numbers. So, but still, the cardinalities of the two sets is the same. And the thing about infinity is, as we know, is that if we add some finite number or subtract some finite number from infinity, it stays infinity. So we really cannot say infinity minus 1 is different from infinity, or infinity plus 1 is different from infinity. The way to compare infinities is actually through this kind of one-to-one correspondence. And that's what we have just done. And we have established that we can create a one-to-one correspondence between the set of natural numbers and the set S, and thus S and N should have the same cardinality, right? Let's do another example. So instead of the set S, now we will consider the set of all, let's see if I can do this, all even natural numbers, right? So let me write that down. So the set of all even natural numbers is 2, then we have 4, then we have 6, then we have 8, 10, and so on, right? So these are all the even natural numbers. And once again, one can establish, so let me erase this older stuff in here, establish a one-to-one correspondence between the elements of the natural numbers and the set E. And the way to do that is pair up 1 in the natural numbers with 2 in the set of even natural numbers, 2 with 4, 3 with 6, 4 with 8, 5 with 10, and so on. So how does this pairing, if we once again try to write down the exact equations for this pairing, how does it work? So natural number n pairs up with 2 times n, 2 times n in the set of even integers, even natural numbers, and natural number even natural number m pairs up with m by 2 in the set of natural numbers, right? So that's how the pairing looks. So 2n in the set of natural numbers, say here 3 in the set of natural numbers, pair up with 2 times 3, which is 6, right? And 4 with 2 times 4, which is 8, 5 with 2 times 5, which is 10. And once again, the thing to observe here is that for every natural number, 2 times that natural number exists in the set E, right? And nothing in E is left out in doing that, and no element in E is matched with 2 or more elements in the set of natural numbers, right? And if we have m in E, that's an even natural number. So m by 2 will be a natural number, and that exists in the set of natural number, and it will be a unique natural number corresponding to m, right? So this ends up creating a one-to-one correspondence between the elements of the natural numbers and elements of E. So this also tells us that the cardinality of the natural numbers, which we had equal to the cardinality of the set S that we talked about earlier, is equal to the cardinality of the set of even natural numbers, which is E, right? So one last thing that we will be doing before that, let me just drag this a little down so that I can make some space for the thing that I'll be talking about next. All right. So the last comparison, that example that we will be doing here, is that of the integers. So before that, once again, the observation that although it seems that the even natural number, the set of even natural numbers, should contain half as many elements as the set of natural numbers, right? Because it doesn't contain the odd natural numbers. But once again, infinities cannot be compared in that way. So infinity by 2 is once again infinity. 2 times infinity is infinity. So you cannot really compare infinities by saying this is half the infinity of the other infinity. So those infinities are, in this case, they are the same as we saw by being able to establish this one-to-one correspondence. The way to compare infinities is to establish one-to-one correspondence. And we saw that the set of natural numbers and the set of even natural numbers, they have the same cardinality because we can establish a one-to-one correspondence between the elements of these two sets. So now the last and final example that we will be talking about is, let's see. Oh, I deleted that, but never mind. So the set of, excuse me, the set of integers. So that's what we will be talking about next. So we know the set of integers contain all the natural numbers as well as the negative integers and 0. Typically one would write 0 and all the positive integers on the right of 0 and all the negative integers on the left of 0. But in this case, what we'll do, we'll write the set of integers in this peculiar way, where we'll start with 0 and then write the first natural number, which is 1, and then the following element will be the negative of that natural number, which is negative 1. Next we'll write the next natural number, which is 2, and the negative of that, which is negative 2. And then 3, and the negative of that, which is negative 3, and so on, right? So let me do this. Let me write a few more elements of from this in the set of natural numbers as well. And so here 1 2 3 4 5, then I would get 6, and I would have 7, and so on. So once again, one can establish a one-to-one correspondence between the elements of the set of integers and the set of natural numbers, right? So here I can pair up 1 with 0, 2 with 1, 3 in the natural numbers with -1 in the integers, 4 the natural numbers with 2 in the integers, 5 with -2, 6 with 3, 7 with -3, and so on. So what's the, once again, what's the equation that I can write down for this pairing? So here, n in the set of natural numbers, depending on whether it's odd or whether it's even, it's being paired up to a positive integer or a negative or zero integer, right? So here, 2 pairs up with 1, 2 in the natural number pairs up with 1, 3 with -1, 4 with 2, 5 with -2, and so on. So if the natural number is even, for example 2, 4, 6, or so on, so it's half of that natural number, right? So 2 is pairing up with 1, 4 is pairing up with 2, 6 is pairing up with its half, which is 3, and so on. So here the relationship will be this. So n pairs up with n by 2 if n is even. Right? What if n is odd? Well, 1 pairs up with 0, 3 pairs up with -1, 5 pairs up with -2, and so on. So if you think over it a little bit, the answer is actually, it's n minus 1 by 2 and the whole negative of that, and that's if n is odd. Right? So that's how element n pairs up with an element in Z, right? So a natural number pairs up with an element in the integers. So n minus 1 by 2, so if I have n as one of the odds, say 5, 5 minus 1 is 4, by 2 gives me 2, and then I take a negative of that, so that's -2, right? Likewise, if I have m in the set of integers, then that will pair up with a natural number, and depending on whether the m in the integer is positive or non-positive, it will pair up with even or an odd element, right? So the easiest one is if m is positive, right? So let's write that down. So this will be so if m is positive, say 1 or 2 in the integer, so 2 pairs up with 4, 3 with 6, so it's just the double of that, right? So this is twice m when m is greater than 0, right? So for example, if m is 3, then it pairs up with 2 times 3, which is 6, right? But if m is less than or equal to 0, say for example here -2 pairs up with 5, 1 pairs up with 3, and so on. So how, what should that relationship be? Well, if you think over it once again a little, then the relationship is negative of twice m, right? Plus 1. So this is for m less than or equal to 0. Let me write that a little clearly. So it's -2m plus 1 if m is less than or equal to 0. So let's just see if that works out for one of the examples. If say m is -3, right? So negative of 2m is -2 times -3 is 6. 6 plus 1 is 7. So -3 pairs up with 7. So this is the way the pairing works for these two sets. And once again, it's not too difficult to verify that this is a one-to-one pairing. That means nothing in the integers is left out and nothing in the natural numbers is left out and nothing is paired up twice, right? So what we have here is this relationship, the set of natural numbers equal to the cardinality of the set of natural numbers is cardinality of the set of integers. And previously we did two more examples where we saw that this is also equal to the set of even the cardinality of the set of even natural numbers and the cardinality of the set of the natural numbers greater than 1. So all these sets have the same cardinality, right? So once again, as was in the case of the even natural numbers, here it appears that the set of integers will contain almost double the number of elements as natural numbers, right? Because integers contain the negative natural numbers, the negative integers as well. So, but the thing is, once again, the infinity is, if you multiply infinity by 2, divide infinity by 2, it remains infinity. You cannot compare infinity by multiplying, dividing by some finite numbers. So the way to compare infinite sets in this case is by establishing or trying to establish one-to-one correspondences um, between the elements of the set. And since we can do that for the natural numbers and integers, the cardinality of the natural numbers and integers is the same. And that the cardinalities of all these four sets that we have talked about are the same, and all these are infinity, but this is a particular type of infinity, and we will see that there are other infinities as well later on. But all these infinities are said to be called countable infinities, and it's written as using a symbol which is called aleph. It's a Hebrew character. Aleph, it looks like a wiggly n with a subscript of 0, right? So aleph subscript 0. So this is this letter is aleph, ALEPH, right? And this is called cardinality of countable infinite sets. Nullity of countably infinite sets, right? So that is aleph naught. So this way of thinking about infinities by establishing one-to-one correspondence between elements, it was first proposed by George Cantor. George Cantor was a German mathematician. G Cantor. Right, I'm not sure about the spelling of George, but so he was a German mathematician who came up with this idea that there can be this crazy idea at that time that there can be different types of infinities. One infinity can be larger than the other infinities. So people knew that if you add something to infinity, it stays infinity. If you divide infinity by 2, it stays infinity. If you multiply infinity by 2, it stays infinity. So here in this case we did compare infinities and we saw that all these infinities are the same, because but the way George Cantor proposed that we compare infinities is by setting up this one-to-one correspondences between elements. So one-to-one, I have been using the word one-to-one correspondence. It's formally called bijection, but this is how you say whether or two sets are of the same size or not, by establishing bijection between elements of between those two sets. So one-to-one correspondence between elements of the two sets. All right, so I think that will be all for this lecture. We will talk about a different kind of infinity in the next lecture.